right, shall we get started? So, how many got question of the day 15? Did you think it was hard? This is a tricky problem. And those of you who did get it, and hats off to you, because it's not immediately obvious. Spent a little bit of time talking about question of the day 15 at the beginning, because I want you to appreciate the subtleties and why many of you had trouble with it. So first of all, I warned you it was tricky. It is, and we'll see why it's tricky shortly. So the homework 1 grades were released, finally. I apologize that it took us so long. We had a couple of issues grading homework 1. I'll tell you, the one that got us the most was that we had split the assignment up amongst the TAs. And I don't know what it is about the icon grading mechanism, but perhaps when multiple people are accessing it, or maybe some of the TAs didn't know they had to click submit to cement their grades kept disappearing. So stuff would be graded. And then day before yesterday, half the grades for 3 of the functions just disappeared from one day to the next. And because we didn't have notes, the TAs had to go grade them again. So I apologize. I think part of the problem was the rubric was not correctly constructed, and that's my fault. But I don't really know if that's the case or not. Maybe a bug, who knows. So they're done. The other thing that held us up, and I'm going to be honest with you, the other problem we had is there are a couple of academic integrity cases in homework 1 where code is clearly shared. And we're still studying those before we decide what to do with it. But if you were sharing code, then you know who you are. And we will report instances that are egregious to the college because we have to. It's not fair to the other students. So that's another thing that slowed us down somewhat. If you feel homework 1 was misgraded, you need to show that it was not graded according to the rubric. You can see the rubric in icon. I don't want to enter into conversations about, well, I think this deserves more points, because it's not up to you. That's what the rubric is for. And the rubric enforces consistency of grading across assignments. So I'm not going to entertain changes to the rubric. It is what it is. Many of you did very well on this assignment, so you should be happy about it. I saw a lot of grades above 55 out of 60, which is fabulous. Some of you struggled. So I did post the solutions, both in Python form and PDF form. You can go look at my reference solution and compare to yours. And if you have questions, we can discuss on Piazza, or you're welcome to email me. Okay, homework 2 will be released by Monday. It's ready to go. I still have a little bit of writing to do, but in preparation, I've posted an article from a publication called Change in Higher Education. And this is a little bit self-serving because I'm one of the authors of the article. But the scheme that's reported in this article is what you're going to implement for homework 2. And the description in the article is, how can I say it? It's not very algorithmic. It's written for higher education professionals who are not computer scientists. I'll give you the short story about homework 2. Some number of years ago, 10 or so, I started working with a faculty member in education on student retention. What makes students leave college, sometimes after the first semester. And we were looking for early warning metrics, surveillance metrics that we could use that tell us that students are not engaged. So at the time, my oldest daughter was a freshman in college. She was a jazz major at a different school. And because jazz band was so reliant on rehearsals in the evening, she rarely ate with friends. She pretty much had to go to rehearsal and then would end up eating alone. And this kid would literally call us and have dinner with us on the phone every night. For a parent, that's really hard, right? Because you're sitting at home, your daughter calls, she's clearly lonely, and she's practicing all the time. We're in rehearsal, and she doesn't have anybody to eat dinner with. So I told my friend, I said, I think that one of the things that makes students want to stay is that they make friends. It's their social network that helps them. Well, you guys have all been through this, right? Freshman year, you meet a lot of new people. You make friends. This becomes your cohort. You eat dinner together. You go out together. You study together. It's what makes college interesting. And if you don't have that opportunity, it's not surprising that you don't retain, you don't stay in college to year 2. Well, to test this idea, I got a bunch of data from the dining halls. The data I got was, at the time you maybe still do this, you swipe your dining card to go through the line. Is that what you do in the dorms? So we had the whole freshman class eating We knew every meal they took. Whenever they swiped their card, we got all the data. So we knew who swiped their card, which dining hall, and what time. And we built a little system that tried to see if we could detect people going to the dining hall together. So if you think about it, when you were freshmen, you'd go eat with people from your floor. You'd all swipe through in the, within a space of a few minutes. Now, that doesn't look very compelling because it seems like, I swiped with a lot of people I don't know. We go through the line together. It's an artifact of going through the line. But over enough meals, and you guys eat a lot of meals, over enough meals, patterns emerge. So we devised a metric, which we call the meal index, or an M-index, and then we looked at how well the M-index predicted retention through graduation. And it turns out that the M-index, as this article explains, is as good as high school GPA in predicting retention of a student in the first year and through graduation, even with only like a month's worth of data. So the first month of school is like the critical time in freshman year where you build your social network. So I'm going to have you write the code to calculate the M-index. And it's a little complicated, but it's an example of a kind of a data science-y problem, which is probably one reason you're in this class, is because you're interested in data science kinds of things. And it's a fairly easy implementation once you understand it. So I urge you, read the article over the weekend. There will be no question of the day today, because I want you to read the article over the weekend. And on Monday, when the homework 2 comes out, you'll have some background to understand what homework 2 is asking you to do. Okay. Question of day 15. So what I'm after here, we've been talking about shuffling algorithm, including the original Cluth shuffle algorithm, what we call scramble, which is a real shuffling algorithm. So other types of shuffling, riffle shuffling, and the other one we did was the random insertion shuffling, which I think was question day 13 or 14. Today we're going to look at a different one called overhand. And if you play cards, we have card players here? The overhand shuffle is where you take the deck in one hand, and then you plop sections of it in the other hand, one chunk at a time. So basically you take the deck and you reorder it chunk-wise. And people will do this with 5 or 6 chunks generally. And people can be very fast at this. If you play cards, you'll see people shuffle this way. And they make multiple passes because it's all about the random length of the chunks. That's what shuffles the deck. So I've simplified this to a 3-segment shuffle. So basically, if your original list or deck has 3 subsections, A, B, and C, and these are of random sizes, then what I want to do is I want to reorder this by putting C first, B second, and A last, but retaining the order of the elements within those subsections. I'm not reversing anything. I'm just reordering chunks. And the key insight here is that this is a lousy way to shuffle a deck of cards if the partitions are always in the same place, because you'll go from ABC to CBA to ABC to CBA and so on. But if the partitions are chosen uniformly at random, and you do this enough, you'll get a pretty good shuffle. And by the way, do you remember that inversion index function we did? Expect to see inversion indices and different shuffles when we start talking about plotting data. So we're going to look at this question today and the other one, and inversion indices, and we're going to plot how many cycles it takes to achieve a good uniform probability shuffle from these different shuffles. Okay, so there's a number of considerations here. First of all, it tells you that you need to modify L. So if you're using concatenation or comprehensions, you're already off to the wrong start, because comprehensions create new structure, concatenation creates new structure. Right? We don't want to create new structure. We want to modify the structure we have. And secondly, we'd really like for I and J to be uniformly selected at random. So let me explain what this is. A number of you fixed the selection of I and J. So you said, well, I is chosen uniformly at random across the whole length of L. But J must be smaller than I, or J must be larger than I. And if you think about it, the chance of getting any of the viable partitions, so you think of all the collection of all possible partitions, you're not going to get all the partitions with the same probability if you restrict one of the one of the variables. I'm not going to grade you down on that, but it's an important consideration because your simplification of the code is causing a change in the algorithm that will affect its performance in the limit, and that's bad. Okay, so here's the first try at this. I've seen this a lot. I saw this a lot. This is actually a pretty good first attempt. What we do is there's a loop here because R is the number of rounds we're going to do. So I'm just going to start with R at whatever it is, and until it reaches 0, I'm just going to keep looping, and I subtract 1 from R each time. So this is a fairly standard way of doing multiple rounds. I'm going to generate 2 random indices. Notice how they're both selected on the same range. Okay. First thing, there's an error here. It should be -1. Yeah. It should be 0 to length -1. This still works, but it changes the selection of the variables for being uniformly at random. And then what I'm going to do is I'm going to rename these as I and J depending on which one is smaller. So this is a common trick. Many of you did this to say, well, be nice to know that I is less than J, less than or equal to J, because they could be equal. So I'm just going to force it to be selected by using min and max. That's perfectly reasonable. You can actually avoid the assignment, but it doesn't matter. And then here's literally C, B, A concatenated together, and then I return a list L. And if you try this, there's a list. It's just the list of the range 0 through 9. If you try this, one round of this overhand shuffle, you'll see that, wow, 0 and 1 ended up here. Wow, those are even reversed. I don't know how that happened. I don't know what happened here. 2, 3, 4, 5, 6, 7, 8, 9. Something's going on here. But notice that the list L, I think this may have happened when I cut and paste. The list L is not changed. And the real problem here is that you use concatenation. You can't use concatenation here. So the next thing is, well, how do I modify L? Well, we know we can use list operations to do it, but we also know we can use slicing. I'm thinking as I'm up here how that got reversed, and I have to think that when I copied the Python buffer into the slide, I messed it up. So I apologize for that. I'll have to try it again. Of course, I won't really know because these are random. It's non-deterministic. So something happened in here, but I suspect it's a copy error. In any case, it does return a shuffled list. It looks like the list is right, but it hasn't changed L, and that's the point I'm trying to make. Okay, so let's try a different way. So here, I'm going to let J, K, and you'll notice I got the links right this time. J and K be the random integers. I'm going to do this parallel assignment, so I get a random integer and a random integer. And then I'm going to use max and min to know that I'm talking about the higher one and the lower one. Okay, so I'm going to let T1 be the sort of last, whatever the larger number is, the tail of the list. I'm going to let T2 be sort of the head of the list. So let's call T2 the head and T1 the tail. And then what I do is I assign to the tail, I assign what was the head, and then I assign to the head what was the tail, and I go on my merry way through the round. So this looks like it's promising because at least I'm not doing concatenation, so I know I'm modifying L. So there's my original list. When I do overhand L, well, it looks reasonable, right? I've got something going on here. Something got moved up here, so it did change it, and it did modify L. So I'm happy because the modification seems to have worked, and all looks fine to me. You'll notice that the reason this looks weird to us is because one of the J and K's was the last element. So you didn't change. You didn't have a tail. You had an empty tail or an empty head. But by and large, this seems to satisfy the requirements. So it looks golden, and this would get full credit. Now let's see if we can make this cleaner. So let's collapse all these excess assignments here. Let's take inspiration from the fact that I can do this parallel assignment and that we've used parallel assignment. By the way, this is called parallel assignment. We have two things being assigned to two things. We've done this a lot. When we want to swap two elements in a list, We often say Li comma Lj equals Lj comma Li, and we're really happy with how that works. It's very clear. It's a nice idiom in Python. One of the nice features of Python, because other languages generally don't have this feature. And now we're going to see why. So I'm going to collapse my code. So I now have jk equals the random length. And I have, this is the head, this is the tail, are equal to the tail and the head. So really, I haven't done anything except take this code here and embed max and min, and all this stuff gets turned into a parallel assignment. Right? So this looks good. I mean, I think I'm onto something. I just need to test it, then I can turn it in. I can be done with question of day 15. I take a list, I call overhand, and something's already clearly going wrong because my list happens to have grown by a couple of elements. So there's something seriously wrong with this, even though it looks like I've just collapsed those excess assignment statements into a parallel assignment. Nothing else has changed. The semantics of these assignments all seem to be clean. It's just an assignment of a slice to a slice. Yet something's gone wrong. If this were to happen to you, you'd start wondering whether Python was broken or what's wrong with your code, and you'd maybe check this against the previous version that works so well. And if you did that, you might not see the mistake. The mistake here has to do with the fact that even though this looks like a parallel assignment, it actually happens one step at a time. Right? So your code from before, this explicitly makes those steps apparent. It's what I hate in all of the beginning code where people say A equals something, B equals something A, C equals something B, D equals something, and it's like step by step by step by step. I get it. It's nice to see those steps. Most of the time, those steps can be collapsed into a single line, and it's just as reasonable and easy to understand, and your code is so much cleaner. But here's one case where when you do that, stuff breaks. So order matters, even in parallel assignment. Let's see if we can figure out what went wrong. The rule for parallel assignment is that instead of evaluating this, remember, when you're doing anything in Python, you first evaluate what that means, and then you assign it to whatever this is. And the issue here is, when I look at parallel assignment, I tend to think, evaluate this, assign it to that, evaluate this, assign it to that. But in fact, you evaluate these two first and then do assignment. So the order of the evaluation is a little bit different. It doesn't matter here because the value of this random integer and the value of this random integer don't depend on j and k. But it matters here because these values depend on what L is. And if you're changing L, that dependency may get away from you. You may be messing yourself up. So let's play with this and see. So here's my first step. I'm just going to create a list, which is the list 0 through 9. And I'm going to randomly generate my own numbers. I'm going to let j be 8. So tail 1 is the tail of the list, and tail 2 is the head of the list. I'm going to let I be 3. I just made those up. Doesn't matter what they are. So if I look at them, the first three elements of, so I'm going to take L3, and I'm going to assign it to T1. So this is the head of the list, which used to be 0, 1, 2, and I'm going to assign it to the tail. So I'm going to replace 0, 1, 2 with whatever T1 is. And if I look at the list, I see that 0, 1, 2, right here, have been replaced with 8, 9, which is what I expect. Then I'm going to replace the rest of the list, which was 8, 9. I'm going to replace that with T2. But something goes wrong. What's going wrong here is that T2 up here is known to be 0, 1, 2. But L8, because I've made changes to L, 0, 1, 2, 3, 4, 5, 6, 7, 8, L8 is only the 9. And I'm going to replace 9 with 0, 1, 2 rather than the originally intended 8, 9 with 0, 1, 2. And this happens because the two random numbers give me a head and a tail that are not the same length. So it makes debugging this very difficult, because if you happen to get a good I and J, it'll look like your code works, and you'll be happy. But if it doesn't, you don't get I and J that give you exactly the same size head and tail, your L is going to grow and shrink. And if I do this enough times, if I set R to 1,000, I guarantee you'll get an error, because eventually you will have lost all of L. So replacing the head of L1 first changes the indexing for the subsequent assignment of T1. So it really is the fact that I made the change here. I changed the head of L first. And because the head of L was replaced with something that was shorter or longer than the thing I'm replacing, when I start talking about index 8 here, it doesn't mean the same thing anymore, because the beginning of the list has changed. So the solution here is just to do things in a different order. And instead of having, let's take a look at what the code that broke looked like. Min, max, max, min. Instead of doing things that way, I do max, min, min, max. Same thing, but now the order of evaluation is sound, and I don't mess up the interpretation of I and J. Now, you could get away with this in different ways, right? You could fix this in different ways. But let me show you, this actually does work correctly. And if I do overhand 10,000, I'll get a shuffled list, and I won't lose any of my elements. Now, you can play with this a little bit, but the error here, or the root of this cause here, is that both J and K, I call them J and K here instead of I and J, I don't know why, both J and K are indexed from the left of the list. And if you start changing the head of the list, the meaning of J and K also change as the list grows and shrinks. If you had used random numbers that index from the right of the list, then the other function definition with the reversed order would be the correct one. All right? So when you're making changes to a structure that you're then going to assume hasn't changed, which is essentially what's going on here, you're going to get yourself in trouble. How many of you had this problem? Yeah, and did you figure it out eventually? So modifying list structure is tricky. And this is what gets you beyond sort of just being able to code something. To be able to think about these things and see these problems, it's a useful thing. Okay, questions on question of day 15? All right, we're going to talk about something very similar to question of day 15, which is variable scoping, which we haven't talked about. This is one of those miscellaneous topics I promised you we'd dispatch fairly quickly. So variable scoping refers to the fact that a name in Python, and by name I mean a variable name or a function name, they are all meaningful only in a specific context, and that context is limited. We call that context the scope of the variable. So, for example, variable names and function names that are used only inside the function only exist inside that function. We know this from the times that we wrote code like binary search that had a helper function. That helper function name is not accessible outside the function. You can call the helper function within binary search, but you can't call the helper function from the REPL because Python won't know about it. That helper function definition is hidden inside the scope of the function. This is also true for variables that are defined in the function. If I have a function definition and I say a equals 15, that value of a is only valid within the scope of the function. As soon as you leave the function, that variable disappears. So let's see how this works. Here's a function definition. I have a variable called x. I set it to goodbye. I return x. And when I call foo, I get goodbye. So everything looks like it works pretty well. But when I ask what the value of x is, I get an error that says, I don't know any x. And the reason we don't know any x is because x is only known in the context of foo, within the scope of foo. So when I'm executing foo, x has this value. But when I'm outside of foo, x has no value. That's all scoping means. Now the problem with this is that it has some real implications with how you code. So scoping rules, like we talked just now about helper or quicksort. So let's take a look at how this works. What happens if I say I define a function foo and I return x, and there is no x inside foo? Where do I find the value for x? Well, I can try typing foo, and I'll see that the value for x was found at the top level. All right? So inside foo, I use a variable named x, but foo doesn't have a variable named x. So Python says, I wonder what this x thing is. And so it looks inside foo first, doesn't find it. It looks at the scope that contains foo, and the scope that contains that, and the scope that contains that, until it reaches the global scope, and it finds a value for x, which it then uses. Now, so at each time you use that variable, Python, or any variable, Python has to figure out which copy of the variable are you using. And as you know from question of the day 15, when I have an L in the calling, as a parameter to a function, right? That L is really a copy of the L at the REPL level, right? But because list structures are shared structures, it points to the same structure. That's how you modify L. If L were instead an integer at the top level, and you change the value of L within the function, that integer value would not change outside the REPL. Only sequence structures, dictionaries, things that have structure, that have multiple things encased in them, can be changed within the function and have it persist outside. So let's see what happens here. I have x is hello. I again define x inside foo to be goodbye. I return x. When I type foo, I get the version of x that is local to foo. But when I type x at the REPL, this x is no longer seen, so I get the outside version of x. Yes, in the back.
Is adding like list structures outside of scope just a Python thing, or is it like very common?
I'm sorry, say again, is what?
Is modifying lists outside of the function scope just like for Python, or like most other languages?
Every other language. So there's in Java, you may have talked about passing by value or passing by reference. Did you ever hear that term before? So things like integers, when I have a function definition that has a variable named x, and I invoke that function with x as 5, right? I'm passing the 5 value as the value of x. It's called pass by value. But if I have a function with a variable L, which is a list, which is meant to point to a list, and I have an outside list and I use that list in the invocation of that function, I'm not passing the function a copy of the list. I'm passing a copy of the reference pointer to the list. So think of every variable parameter as being passing a location in memory, if you like. For integers, that location in memory, it's just the integer. But for a list, it's where the list is located. So making changes to the list persists outside. We'll talk a little bit more about that actually in just a few minutes. But this is a subtle difference, and that's why so many students have trouble with modifying lists rather than just modifying the internal variable that points to the list. Okay? Has anybody heard pass by value, pass by reference before? A few of you have? Okay, so. All right, so local variables inside the scope of the function that share the name with variables outside the scope of the function, we say those variables shadow the outside variable. So this x here is really shadowing the value of the x outside. When I'm inside the function, it gets this value. As soon as I leave the function, it reverts to the original value. It's hidden. The original value is still there, but it's hidden from foo because I have a local copy. Okay? So this is important when I write recursive functions, because in a recursive function call, every time you invoke the function again, it's like having a fresh set of parameters. Right? If you have a recursive function that's recursing down a structure S, each invocation has its own copy of S, its own pointer to the S structure. Let's look at a more complicated example. I have a variable at the top level called z. Inside foo, I have a variable y, and y is set to good, and I return the concatenation of y and z. Well, y is local to foo, but there is no z inside foo, so I use the global version, and I get goodbye, as you'd expect. Z has a value because it's a globe, it's external to foo, but Y still only has its value inside foo. So all of this sort of makes sense, or it should. Is everybody okay with this so far? So you can mix what we call global variables. This Z here, defined at the top level, is a global variable. You can mix those with local variables. This Y is local to the function foo. It's inside the scope of foo. Let's try this again. X is bad. I'm going to invoke foo, but this time I have a parameter in foo. So this formal parameter x looks like a variable with scope of foo. Even though it has the same name as this outside variable, this formal parameter also shadows the value of x. Now, bad is not the default value of x or anything like that. I'd have to do that inside the parameter list. It's just this variable is a separate variable called x that's different from this x. The outside x is global, the local variable parameter is local. So otherwise it's the same. If I invoke foo with good as the value of x, I get goodbye. If I invoke foo with x, then what happens here is that the variable values are first evaluated. So x is evaluated at invocation. The invocation is outside the scope of foo, so I get bad, and I get back bad by, and x itself, of course, is still the global variable. So notice that bad is not the default value of x or anything like that, but when I invoke it explicitly mentioning x, at invocation, this x is the global x, not the global x of the function. That is always the case. The formal parameters are evaluated at invocation in the context outside the function, and then they can be used in the context inside the function. So this magic moment when you invoke foo, we get a transfer of values from the outside world to the formal parameters in the inside world, and they can be evaluated there. So function invocation is this mapping of outside scope variable values to inside scope variables. Function passing does that, or variable invocation does that. Let's try another one here. Define function foo. If x is equal to hello, print this. Otherwise set x to high and print x. Now let's look at foo for a moment. The first use of x here is in a conditional statement. This is not an assignment to x, it's a test of x's value. But x doesn't have a value. So here, when I'm checking this, it says, wow, I don't know of any x. X doesn't have a value, so I'm going to give an error that says that x is a local variable and it's referenced before its assignment. Here's the assignment to x. It happens afterwards. So this confuses Python. What is x? Is it global? Is it local? I can't resolve it. So whenever you see an x inside assignment inside a function like this, Python recognizes x as a local variable. Why? Well, it's not a formal parameter of foo. And inside the scope of foo, I can't change the value of a global variable anyway. I'm not allowed to. So whenever you see a variable name on the left-hand side inside a function that you don't recognize, Python says, hey, that must be a local variable to foo. And by the way, you're using it here before it's assigned, so I'm going to give you an error. So I would like to have some way of telling Python that this x is not a local variable. And I can do that by using the directive global. So let's take a look at this. X is now set to some global value. And I have a function in definition foo with no formal parameter x. And I'm going to use x inside the function. But I want to tell Python that the x I'm talking about is not local to foo, but is the x outside foo. It's the scoping, it's the outside scope x. It's the global x. And I can do that by declaring x to be global, which tells Python, hey, you're about to assign to x, but that's not just some local variable. This x is the x from outside. So now when I invoke foo of by, I get good plus w, which is goodbye. And look at this. The value of x, which was go away, is now good. Because this assignment to x is to the global copy of x, not the local copy of x. All right, is that clear to everybody? So that global directive changes everything. It tells the Python interpreter That x is not the local variable you think it is. It's global. So using global tells Python how to make sense of x. And that means once you've said that this is the global variable, any assignment is now permanent to the outside world. Now the question before about the list, this doesn't apply to lists. Lists are always going to be any structure that you pass in. Modifications made to that structure are to the only global copy of that structure. What's local is the pointer to that structure's name. Okay, so here's where you can get into trouble. People often write code and resort to having a bunch of global variables in their file. Why? Because it's easy. If I'm writing a larger program like Homework 1, what's the harm I'm trying to remember what was Homework 1 again. It was a card game or something. What's the harm with having the deck variable be global? Doesn't really matter. Let's make it global. I don't have to pass it around in a parameter list. But this is bad. It's very bad practice. So we want our functions to communicate with each other by invoking each other and returning values. And that means that they need to be self-contained definitions. If the function's execution depends on some outside global thing, then you can have other functions change the behavior of your function by fooling around with your global variables. So it's sort of a question of style, but it's good not to rely on global variables. Global variables can be used promiscuously, and it can cause your code to break, and it can be very, very difficult to track it down. So because other functions that other people write can come in and change your global variables, imagine that you're writing a card game and you use a global variable called deck, and you load some library that lets you print out cards or show them nicely on the screen, and it also has a variable called deck, and it blows away your variable, your game's going to break. So keeping your stuff privately is good programming practice. These globals are called promiscuous variables sometimes, and the other term in software engineering is called global stamping. And they're very bad ideas. Promiscuous variables should make you think, where has this variable been? Is it got something in it? Is it a value that I can't predict? I don't control the value of that variable. We don't want to do that. So avoid referring to global variables in your code if at all possible. Okay, it's complicated. Bunch of caveats. So this is the question that was asked about lists. Mutable structures, like lists, when passed as arguments, are not replicated. They're shared as if they're global, but the name is not. So some of you in question of day 15, you took this list variable, and the first thing you did is you redefined L to be list of L. Well, list of a list generates a new copy of that list. And the first thing, if you do L equals list of L, you're doomed to failure now. Because any modification you make to L will not be to the L referred to from outside, but will be, by definition, to a local copy of L. And that's why your code doesn't work. All right? So the pointer to L, the name of L, is local, is private, but the thing it names, the thing it points to, the thing it refers to, the reference, is still global. Mutable structures are not copied also because they can be quite large. If I had a list of 10 billion elements, and I invoke a function, I write a function that says, what is the third value in the list? And it takes L as its argument. Every time I call that function, I don't want to copy a billion elements. I'd rather just copy the reference to that list of a billion items and find the third element there. So there are good reasons to pass by reference instead of passing by value. Python makes this distinction easy. It does for mutable structures, it passes by reference. For other items, integers, floats, and so on, booleans, it passes by value. Does that help? Was it clear? Okay, we can share variables within local definitions. When we wrote bin search, do you remember this? We had a helper function inside. The helper function referred directly to the variable L without having L in its passing convention. It could do that because the helper function was defined within the scope of bin search, And so the variable L it refers to is the local L of bin search. So go back to the bin search, go back to the quicksort. You'll see this kind of variable sharing when defined within the function. There's a name for this, a fancy name for this. It's called encapsulation. We're going to get to this like next lecture when we start talking about object-oriented programming. It's one of the organizing principles of writing with objects. Now I want to point to this very nice tool, pythontutor.com. It lets you do some typing to the REPL, and it shows you visually what's actually going on. So if you're struggling understanding this difference between a mutable structure being passed or an integer being passed, just go type. You should go type the example that we did for question of the day today, that sequence of items. Try that in Python Tutor and you'll see what's going on. Okay, so that's it for variable scoping, and I promised you that we would cover object-oriented programming next, so let's do that. So what is how many of you have heard the term object-oriented programming before? Okay, so you know what this is. Most of you learned about it in Java, I assume. C++ as well. Smalltalk, probably not. There are a bunch of object-oriented languages around. It's kind of a change in philosophy. In the early days of computing, of course, we wrote machine code because that's all we had. There were no compilers. So people wrote whatever the language of the machine was. All their code was written specifically for that machine. Get a new machine, start writing over again because it's all different. In the late 50s, we started seeing early generation languages where I could write in a portable dialect, and there would be a tool, either a translator, interpreter, or a compiler that would take my code and convert it to the machine language of the machine. We saw this on the first day of class in that stack, so that I could run my code on multiple machines. And the very earliest languages we saw, anybody remember the early languages? Want to guess? Very earliest ones? No idea. Fortran, late 1950s. Fortran was probably, formula translation was probably the first. Lisp, another AI language still in use, 1957. It's as old as I am. COBOL, you probably heard, 1960. Those are the early languages. And those languages were not very sophisticated. In particular, the facility for invoking other functions, doing recursive calls, they were pretty primitive. And so what happens is, in some of those early languages, and maybe you wrote some BASIC when you were a kid or saw BASIC, they would allow you to write code that was like step by step by step, and then abruptly branch to a particular step number and then proceed from there, and then abruptly branch somewhere else. So code became a series of sequences with go-tos to other sequences and go-tos back in the first sequences. And what happened is, as code became more complicated, nobody could keep track of the flow of execution in the code. It was impossible. Refer to that kind of code as spaghetti code, because it was just like this mass of pointers, really messy, hard to understand. And it's just bad code, right? So there were a couple of efforts, many efforts, to sort of enforce the avoidance of spaghetti code by imposition of programmer discipline, basically. Don't do that. There's a famous paper by Dijkstra, the guy I mentioned the first day of class, and the paper's title is "Go-To Considered Harmful." So he argued that we shouldn't have go-to statements in higher level languages. And to be fair, we don't have those anymore. They were common in assembler, but not in higher level languages. But around 1970s, maybe 10 years later, there was a seminal new language called Smalltalk that saw writing code as a different sort of exercise. In the imperative languages, think Fortran, C, and so on, we mostly think of steps that we take and maybe repetitions of steps or maybe function calls. All of the 5 algorithmic rules we have for analyzing runtime, they basically come from this imperative programming philosophy. Fortran, C, those are imperative languages. Okay? But some people in the 70s started thinking, well, maybe we should think of programming as, I have this thing that is competent for representing some data and doing some operations in that particular type of data. So think, I have a list. A list can manage lists, it can print them out, it can change elements, it can add elements. It can take care of itself. And if I want my list to do something to another piece of data, what I'll do is I'll send a message from my list. My list will tell my integer, add 7 to yourself. And so we had this brief moment where everybody started thinking about programming as things that were talking to each other and sending each other's messages. So I'd say in the message to Ben here, I'd say, add 7 to yourself, and he'd come back to me and say 13, right? Because his current value is 6. And this is how computation proceeded. The original idea was that if I had someday a network of machines that were all independent, I could program in parallel by just having this paradigm for doing things in an object-oriented way. That did not work out. But this paradigm of object-oriented languages had some advantages. And one of the advantages, it made clear who data belonged to, and it got rid of promiscuous variables. You cannot have promiscuity in an object-oriented language. If I want to change Ben's value, I got to tell him, Ben, you're now 17. I can't just change it on the sly and surprise him, right? With global variables, I could change something and his own value would change. He wouldn't know it. But this way, everything belonged to somebody, and there were very circumscribed boundaries about what you could do to different pieces of data. And that's the beauty of object-oriented languages. Had a couple of really nice concepts. The first one is the one I'm describing. It's called encapsulation. Data belongs to somebody. Nobody else can touch it. Second one is polymorphism. That's from the Greek poly for many, morphism, morph for form. It means that things take many forms. We've seen a sort of a basic example of polymorphism when we use the plus sign for concatenation on strings, but for addition on integers or floats, right? So plus has many forms. For strings, it's concatenation. For numbers, it's addition, and so on. And the last thing is inheritance, which I haven't really talked about, but the inheritance says that if I have a generic, a particular type of data, let's take dictionaries for example, I can create a special type of dictionary that doesn't have values. Call it a set. And the implementation of my set can be pretty much borrow from the implementation of the dictionary. In fact, it doesn't have to borrow. I'm going to implement the set as a dictionary with some specialized additional features. And so I don't have to start from scratch every time I want to implement something new. I can start from something similar and modify it and then get the new functionality I'm after. So these are the 3 basic premises of well-written object-oriented code. And the main advantages that these promised was that I could write large, complicated systems by focusing on the little parts at a time, and that the code that I write would be more robust, more maintainable, and more transparent. Those were the big promises. And some of this was actually true, but not all of it. All right, so we're going to embark on object-oriented programming next time, and I'm going to show you object-oriented programming in Python. So one of the things about this class is you've seen a very imperative style of programming, like Fortran or C, where step, 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 like question of the day 15 is. You've also seen a very functional style of programming where functions don't make any changes to data, they just return new values. That's like languages like Haskell, which you'll see again when you're a senior. And now we're going to see the object-oriented style of languages. Those 3 language styles comprise all of the languages that are common usage today. Any language is typically more or less one of those forms. Sometimes they blend or mix types of those forms. All right, I think we're done, right? Yep. No, we have 2 minutes. Any questions? You know what? I'm going to stop here because I don't want to do this. Yeah, I think this is better done with a whole lecture. So I'm going to stop here and pick it up on Monday. Please read the article. You'll be at a disadvantage if you haven't read it.